I want to introduce you to a tool which might be useful to you as a visual way of understanding the genotype frequencies that you expect to see in a randomly mating population. It's called a Prout square. And I'm standing this square on one corner so that you don't get it confused with a Punnett square. They're different things, they're meant for different purposes, and if you get the two confused, you're going to answer a bunch of questions wrong on your exams. So the Prout square stands on its side like this. And let's suppose that in the population that you're dealing with, you've been told that the frequency of one allele, the A1 allele, is 0.7 and the frequency of the A2 allele is 0.3. How do you use a Prout square to visualize the genotypes that you expect to get? Well, you can imagine that there's a scale running along each one of these upper edges from 0 to 1. Those are the possible frequencies that you could have. You could have a frequency for the A1 allele that's as low as 0 or as great as 1. This side of the square represents the probability that the mother of any particular individual in the population donated an A1 versus an A2 allele. So because P is equal to 0.7, what we're going to do is we're going to start here at 0, we're going to go down all the way to 0.7, and we're going to draw a line across the square starting right there. Okay, so this is the probability that mom donates an A1 allele. This is the probability down here, it's smaller, that mom donates an A2 allele. It's the same thing for dad, so we're going to go over this side of the Prout square, and we're going to walk down here and draw a line. Okay, so dad donates an A1 allele with a probability of 0.7, donates an A2 allele with a probability of 0.3. The areas that you're seeing out here correspond to the probabilities or the frequencies that you expect to get for the different genotypes. Okay, up here, p squared is 0.49, that's nearly 50%. And you can see that nearly 50% of the area of the square is in this cell. These are A1A1 individuals. Half the individuals in the population should be A1A1. Down here, A2A2s should be relatively rare. Only 9% of the area in the Prout square is contained in that cell. You have to add these two together. These are the heterozygotes. There are two ways to get heterozygotes. So you have two cells. Together they add up to 42%. Okay, you can see just by kind of looking at this square what relative frequencies you'd expect to get, more or less, for the genotypes. A perfectly valid question to be asking at this point is, why would I do this? Why would I want to visualize genotype frequencies in a randomly mating population? Well, there are some questions for which this is useful. We're actually about to get into one of those questions, which is why I showed you this tool. Let's take a look at where the alleles are found, which genotypes the alleles are found in this population. So every heterozygote, that's those individuals in these cells, has one A2 allele. Every homozygote down here has two A2 alleles. We can sketch out the math pretty rapidly. Let's suppose there are 10,000 individuals in this population. That's 20,000 alleles because each individual has two alleles. There are going to be 6,000 A2 alleles because 6,000 is 30% of 10,000. 0.21 plus 0.21, that's 0.42, or 4,200 of those alleles will be found in heterozygotes. Only 1,800, that's doubled because each one of these individuals has two A2 alleles, are going to be found in homozygotes. In other words, 30% of the A2 alleles will be found in homozygotes. You don't actually have to do that math to just get a sense of, okay, this is the size of this cell in the Prout square relative to these. Okay, I'm going to find a reasonable number of the A2 alleles in homozygotes. Why does that matter? Why is that useful? Well, let's change the frequencies a little bit. Now the A1 allele is at a frequency of 90%, and the A2 is at a frequency of only 10%. Okay, again, you don't have to do the math to realize that this square is a lot smaller relative to these compared to this Prout square here. So it looks like fewer of the A2 alleles are being found in homozygotes. You do the math and it's true. Here we've got 30% of the A2 alleles show up in the homozygotes. Here it's only 10%. If you keep going, it gets even more extreme. A minuscule number of the A2 alleles are found in homozygotes when the frequency of the A2 allele gets down to 1%. What's the take-home point from the Prout square? Rare alleles are mostly found in heterozygotes. So when an allele is rare, you pretty much only find it in heterozygotes. When it is common, it shows up in homozygotes a lot. And when a frequency of an allele is near 1, near 100%, almost all of them are found in homozygotes. So natural selection is only really acting when one allele, on average, has a higher fitness than the other, when different genotypes have different fitnesses. And what you want to focus on when you're worried about how natural selection is changing allele frequencies in a population is what's the fitness of the heterozygote compared to the two homozygotes? Okay, there are three possibilities. The heterozygote could be the most fit of the three genotypes. In that case, you'd see a diagram that looks like this. Here, the dark blue bar is the fitness of the A1 genotype. Heterozygotes here in the middle, and the A2 homozygote is least fit. The fitness of the heterozygote could be in between the two fitnesses of the homozygotes. And finally, it could be less than the fitness of either of the two homozygotes. Okay, the outcome of natural selection on allele frequencies is going to be different depending on which of these three scenarios you're dealing with. A tool that you can use to predict the outcome of evolution by natural selection on allele frequencies is a graph that looks like this. On the y-axis, we've got the mean fitness in the population, and here we've got the frequency of the A1 allele. The population will evolve, in other words, the frequency of the two alleles will change until this is at a maximum. One thing that you can do when you're tackling a mathematical problem in biology, or anywhere else for that matter, is sometimes a quick and dirty way of solving it is to think about the extremes. In this case, the extremes are what happens when the A1 allele is really rare, and what happens when the A2 allele is really rare, i.e. when the A1 allele is near a frequency of 1. If the A1 allele is really rare, the mean fitness in the population is going to be right about here. It's going to be around about 0.6. What happens is you add A1 alleles as you kind of move out this way along this axis. Well, every heterozygote is more fit than each one of these A2 homozygotes. So as you add more and more A1 alleles into the population, you're going to get more of these heterozygotes, and the mean fitness of the population is going to go up. So we're going to see a line that starts here, and it's going to go up. You know, we don't know exactly what the slope is. It might go like this. It might go like this, but we know it's headed upward. Over on the other side, A1s have a relative fitness of 1. Over here, the few A2 alleles that you see in the population will exist in heterozygotes. And remember why, if you look back at that Prout square, when an allele is very, very rare, it's almost always found in heterozygotes. So you've got these heterozygotes here. They're much less fit than these homozygotes. So if you add more A2 alleles, the mean fitness in the population goes down. What that means is that you start here, and as you move this way out along the axis, this line slopes downward. So we've got a line that starts here and slopes upward. We've got a line that starts here and slopes downward. It doesn't take much imagination to fill in what happens in the middle. There's a line that constantly slopes upward, going from here to here. Okay, how is a population going to evolve if this is how mean fitness changes as the frequency of the A1 allele changes? Well, as I said, under natural selection, allele frequencies change in such a way that the mean fitness of the population goes up. It's going to go uphill. In other words, it might start here, and it's going to go like this. And no matter where the frequency of the A1 allele is, no matter what the frequency of the A1 allele is, natural selection is going to keep pushing it higher and higher and higher until finally it drives the A2 allele extinct. Now, one thing I want you to notice is it doesn't really matter what the fitness of the heterozygote is as long as it's between here and here. If the fitness of the heterozygote is down here, this line is kind of bowed, but it's still always going to slope upwards as you go from left to right, which means that the A1 allele is going to become fixed in the population. If the fitness of the heterozygote is up here, it's bowed the other way, but still it slopes uphill going to left to right. In any of these cases, no matter where the fitness of the heterozygote is, as long as it's in the middle, the A1 allele, the allele that is more fit, is going to go to fixation. That means it's going to go to a frequency of 1.0. So that's one of your outcomes. When the fitness of the heterozygote is in the middle, the most fit allele always goes to fixation. Now let's take a look at the other two cases. These are more unusual, and they're kind of strange. What happens when the fitness of the heterozygote is higher than the fitness of either homozygote? Go ahead and answer this question on your own, and then come back to this video. Try to use the method that I just used in the last example. Figure out what's going on at the extremes when the A1 allele is very rare and when the A2 allele is very rare.